So we actually have a numerical way of measuring the strength and direction of a linear association. Now I need to emphasize that what we're about to talk about, which is called correlation, can only be used to measure the strength and direction of a linear association. So that is something that needs to be emphasized, as students tend to forget. But there's a calculation that can be done with these data values that can produce what's called the correlation coefficient. Most of the time, we're going to let the calculator do it, but just to kind of give you a brief overview, on the next slide I'll talk about, and again, very, very briefly, how it's calculated before we actually do it and use it to describe the strength of a linear association. I will say here at the outset that it really is a measure. So let me just make this number line here. It's a number. So what's called the correlation coefficient is a number, and it ranges between -1 and 1, where 0 indicates that there is no correlation. So the closer once we calculate this thing called the correlation coefficient, anytime you get a number close to 0, that basically says that the relationship between the two quantitative variables is not linear at all. Okay, the closer it is to 0, the more non-linear it is. If you get -1, which, I mean, you'll never get -1, but if you get something close to -1, that is a very strong negative correlation. -1 is perfectly strong. This is a perfectly strong, or meaning as strong as it can be, negative correlation. And on the other hand, if you get 1, 1 would just basically mean all the points line up in a line, as though you were graphing something in a pure math class. And -1 would also be in a line. A correlation coefficient of +1 means that basically the slope is positive. It's a positive association. So the correlation coefficient is a perfectly strong positive correlation. So in the next slide, I'm going to just give you a brief overview of how this is calculated. So what's done is you standardize both variables. In other words, you find the mean of both variables, and once you find the mean, you take every point, and you first focus on the explanatory variables, and you find the z-scores for every single one of those, and then you find the z-scores for every single one of the response variables. And when you do that, you've basically, regardless of what the units are, because we can compare two quantitative variables that have two different units, regardless of what the units are, once you've standardized them, they are both in terms of standard deviations, right? They're in terms of z-scores. So you're comparing the z-score of one quantitative variable with the z-score of another. And so it has no units. When you do that, the overall shape of the scatter plot won't change. But what you will do is you'll convert the mean point, meaning the point that is the average of the two, that becomes the origin. Okay, and we'll see in the next picture what we do from there. So here again, we just to emphasize that the original variables are here on the right, and you can see the shape. On the left are the standardized variables, so the shape is identical. If you note that the x and y axis have different units, it's because the one on the left is a standardized representation, meaning it's in terms of z-scores. So, but the point to emphasize is that we haven't changed the relationship by normalizing or standardizing. And so here's how we calculate what's called the correlation coefficient. And again, wouldn't get too caught up on this calculation, but it does make sense. I mean, there is a kind of a nice logic to what this is doing if you just take a second to examine it. Basically, this point here is the mean line, meaning that's where the coordinates representing the averages of the two variables are. In order to measure the strength of a relationship, we note that if it's a positive relationship, we expect the direction to go from bottom left to top right, which means that we want to count all the points in those two quadrants as being part of a positive relationship, right? They would be adding to the relationship by, suggesting a positive relationship. And so what you notice is that in that case, anything in the top right quadrant, both coordinates are positive, okay? And anything in the bottom left quadrant has that both coordinates are negative. So if you multiply the x-coordinate times the y-coordinate and do that for every single point, and then sum, and then divide by not quite however many there are, it's just a slight adjustment, but pretty much an average. What that does is it counts all the things in the top right and the bottom left as being positive. The product would be positive, and anything in the top left and the bottom right, where the coordinate signs are opposite, will count as negative. Okay. Now, if there are more points in the top right and the bottom left, well, then that means that overall the association is positive. So the more positive the R value becomes, the more it's indicating that you have many points in the top right and the bottom left. On the other hand, if you get a strong negative correlation, that means there are many more points in the top left and the bottom right. So this relationship here, again, by multiplying the x and y coordinates, summing them up, and then basically averaging that, or finding the average of that product, you're sorting out where, in a quantitative way, where those points are. Are they generally bottom left and top right, or are they generally top left and bottom right? So that's what the correlation coefficient calculates. So as we go forward, just notice it's a number that's basically telling us how the scatter is situated in terms of these quadrants here.